Okay. I think our projector's going to die. It sounds horrible. We only hope it lasts to the end of the school year. Okay, so talking about continuity, we have a few questions to discuss. In the reading, from the reading, does a value of f of x not have a bearing on whether f has a limit at x naught or not? This was from chapter 2. Did the value of f at that point determine whether it had a limit at that point or not? Not really, huh? Because remember, if this is x naught, it has a limit if it can approach the same value from both sides. So if it's coming down to or up to it, f doesn't have to be defined there. It could be defined to be something else there, but it still has a limit. So the limits did not depend on f of x naught. We had three types of discontinuities or breaks in our limits. Do you remember what they were, the three types of breaks and limits? Okay, we have a jump. You have a vertical asymptote that approaches. The horizontal one, that you can have horizontal asymptotes, but that doesn't break your limit. If the vertical asymptote, usually what happens is you have something comes like that, and then down here maybe something comes like that, and they go to two different values, so you don't have that limit because of your vertical asymptote. And then the last one, remember our sine 1 over x function? And it just goes up and down really, really fast. It didn't have a limit. So that last one is erratic behavior in the function. No. Yeah, it's very erratic. It jumps high and low rapidly. It oscillates rapidly. Or oscillates. How do you spell oscillates? OSC oscill 2 L's?
Yeah.
Yeah, we'll go with it. Oscillates rapidly. So those were the three problems that we saw when we were looking at limits. Those are going to give us same problems when we look at continuity. Our definition for continuity, you should know this definition. It says, suppose E is a subset of the reals f takes E to R. If x naught is in E, then f is continuous at x naught if and only if for each epsilon greater than 0, there's a delta greater than 0, such that if x is in E, such that if x minus x naught less than delta and x is in E, then f of x minus f of x naught is less than epsilon. I got the wrong epsilon symbol here. If f is continuous at x for every x in E, then we say f is continuous or continuous on E. Keeping that in mind, what's the definition for a limit? Suppose D is a subset of R, f takes D to R. Here's the first difference. X naught is an accumulation point of D. If x naught is an accumulation point of D, did x naught have to live in D? No. Okay, so x naught might not be in D. Okay, then f has a limit L. Notice that this is not necessarily equal to f of x naught because we don't know that f of x naught exists. So limit L at x naught if and only if for each epsilon greater than 0, there's a delta such that, here's our last requirement that's different. 0 has to be less than x minus x naught. Less than delta implies f of x minus L is less than epsilon. So very few differences. In continuity, you have to know x naught lives in D. You have to know the limit is equal to f of x naught. And you don't assume 0 is smaller than x minus x naught because we allow x to be equal to x naught. So that's the difference. They're very, very similar. They're very, very similar.
But still, symmetric absolute is always equal 0 or greater.
It greater than or equal to 0. Yeah, it could be equal to 0. Mm-hmm.
I would assume the definition of continuity would be a good question to ask on the test.
Oh yeah, along with the definition of limit. Oh yes, yes indeed. Good definitions to know. Question: what does the definition of continuity mean? If you were drawing a picture, this was our definition, this was our limit picture that I put up here. So what is the difference? This L is f of x naught, and this point right here, instead of being a possible hole, that's f at x naught. That's the only difference. You turn that L into the f of x naught. So the picture for continuity looks very much like the picture for limit, but the only difference is that you actually know that x naught's in the domain and the limit has to be f of x naught. So for continuity, what we're going to find out is the limit as x goes to x naught, f of x is equal to f of x naught. We're not proving that claim today. Continuous. I don't like writing all that stuff out. Well, we are proving it. That's going to be in one of our theorems. I take that back. It's not in our definition. That is our equivalence theorem. I had to think about that.
Yeah.
I've gone over so many sections. I'm not quite sure which one we're at. Yeah. That's there. Okay. You have some homework problems that are going to ask you to prove that your function is continuous. I want you to do the epsilon delta proof. So we're going to do epsilon delta proof for continuous here. It says, use the definition of continuity to show that f of x equal to x is continuous at -2. I need a P. So our hypothesis is f of x equals to x. Now, our next, that's all for the hypothesis. Then our next step is to fix epsilon greater than 0. We have to figure out what delta is going to be, and we'll fill that in a minute. Then for all x in the reals with, now don't put the 0 less than, just do x minus a -2 less than delta we have. And this, let's calculate it. F of x minus f of -2. What is f of x equal to? X. What is f of -2? -2. So that's x plus 2, but that's the same thing as this value right here, right? So I know that's less than delta, so what should we choose delta so that we get epsilon for our answer? Yeah, well, we'll just make it equal. Let's try that. And so, what's our conclusion? F is continuous.
Wait, that's it?
It is.
Doctor.
We have to start with an easy one. We have to start with an easy one.
Doctor, it's already give all the hard ones on the in class, all the easy ones
On the homework? I saved the easy ones for the test.
Okay.
Or you can say both for the test and
Okay, so another one. Use the definition of continuity to show, now this is a parabola.
yes.
So what's the hypothesis on this one?
But after that, equal x squared.
Yeah,
That's it.
that's the hypothesis. What's our next step? Fix epsilon. Great. Oh, that looks like part of the fix. Let's try again. Fix epsilon greater than 0. Let delta equals something. We don't know yet. Then for all x in the reals with, now here again I have minus 2. So x minus a minus 2 less than delta. We have, and let's do our arithmetic. I'm actually going to give myself a little bit more space. F of x minus f of minus 2. What is f of x equal to?
X squared.
What's f of minus 2 equal to? 4. So I have x squared minus 4. This value, yeah, exactly. This is an x plus 2 right here. So when I factor this, this becomes x plus 2, x minus 2. And I put them both in their own absolute value. X plus 2 is less than delta. I need to find a bound for x minus 2. Okay? So if I know x plus 2 is less than delta, I'll put I'll put it right here. Calculate this, that means this becomes x plus 2 less than delta. I want a value for delta. I want delta to be less than 1 and something. So I'm going to make that smaller than 1. Because what I'm going to do is write what that means. I have a minus 1 is less than x plus 2 is less than 1. Let me reset now. But what does that mean? I'm looking for an x minus 2. Well, I'm going to actually subtract 4. If I subtract 4 from a plus 2, what do you get? Minus 2. I'm trying to get this x minus 2 right here. But this is a minus 5. That's less than an x minus 2 is less than a minus 3. So then the absolute value of all of this should be less than what? Less than the biggest of the, if you take the absolute values of everything. It's going to be smaller than the biggest. So x minus 2 has to be less than the absolute value of minus 5, or x minus 2 is less than 5. And then I'm going to plug it in. And so, if you know that x minus 2 is between minus 5 and minus 3, what happens when you multiply everything by a negative sign? Yeah, and then that tells you that 3 is less than x minus 2 is less than 5, a minus x minus 2. So if you're looking at positive values, the absolute value has to be a positive number. So it's going to be between 3 and 5.
Then wouldn't that make it a 2 minus x?
It doesn't matter inside absolute value. 2 minus x is x minus 2. Yeah. And now I'm going to plug it into my arithmetic. So I come down here, and that x minus 2 is going to be less than 5. So I have delta times 5. What do we need to make delta be to get epsilon? Yeah, epsilon over 5, right? And notice I made it the minimum of 1 and epsilon over 5. Just in case someone chose epsilon to be 100, and epsilon over 5 is now bigger than 1, I still have to choose it smaller than 1, because we chose the 1 right here. No, because it has to work for every epsilon, and as soon as you choose a value for delta that is just a number, I'm going to choose an epsilon so small that your delta value won't work. Yeah. It has to have this. Oh, we have. We did it in limits. Yeah, you'll remember when you go back and look at your notes. I promise you. So what's our conclusion then?
F of X is continuous. And
Yeah.
X not.
There's our proof. And that one was a little harder.
Too much harder.
Not too much harder. Yeah. All you have to do is after you factor, you have to realize that you have to bound the other term that doesn't depend on delta.
This is all we're doing on the homework.
You have a couple of problems like this, and you have a couple of problems that aren't quite like this.
So we have 10.
Yeah, no, there are not 10 homework problems. Kalai. Kalai is wanting me to assign 10 homework problems.
July, you can do the 10 homework problems, I'll do one of them.
There were only 2 because I didn't like any of the others, and there wasn't much good ones to
Wait,
choose from
only-
on the last homework assignment. Yeah, there were only 2 because I didn't like the
I thought you said
others.
there was only 2 of them.
Oh no, there's 4 in this one. I'm pretty sure. Normal
I'm
number.
like, praise the Lord, and there's only 2.
Actually, be very worried if it's only 2. That
They
usually means
they
I
have
won.
11, I said 10.
They have 11 to choose from. Yes.
You do all 11, tell us how it goes.
Okay, so let's look at number 4. I'm doing one of them for you, Kalai. If x naught is in E, x naught is not an accumulation point of E, and f takes E to R, prove that for every sequence xn converging to x naught with xn in E for all n, f of xn converges to f of x naught. It looks kind of confusing. So let's figure out what's the hypothesis.
Assume Assume hypothesis.
And let it not be an accumulation.
Yeah, I need to get the function.
I didn't want you
Accumulation.
to run onto these, so they're not supposed to do that.
Yeah, there you go. Accumulation point of E. Okay, let F take E to R. And we need to let Xn converge to X naught. Mm-hmm. I wrote it in different notation than they did, but it means the same thing. Now, right about now, you should be really confused because what did they tell you X naught was not? It's not an accumulation point. What does it mean to be an accumulation point?
This is Q is the.
I know. I'm looking to see if you know. No.
That's where Q is
I
the
think I
subset.
gotta sit down and like work on it. I still don't know.
That is a byproduct of being an accumulation point. What's the definition?
Number A is an accumulation point of S if only if every neighborhood A contains infinite many points of S,
Yeah,
where S is
yes. S is different from A. So you contain infinitely many points in S different from A. X naught is not an accumulation point of E. How many terms of that sequence can be really close to X naught?
Can be,
infinite.
but the X naught can be in. or
X
can be
naught
out.
is in E,
Right.
but it's not an accumulation point. That means every sequence converging to X naught has to have an infinite number of terms that is X naught. They can't be different from X naught because it said different from X naught. It's not an accumulation point, so those values are not going to be different from X naught. So tell me about this sequence. Since X naught is not an accumulation point, me draw you a picture. Here is your set E.
Looks like a flag.
It does sort of. That's our set E. Our set X naught is going to live inside E, but it's going to live in its own little neighborhood that is outside of the domain. So everything here and that point is our set E. Everything in that little pond around our point X naught is not in E. That's what it means to not be an accumulation point. It's a point that lives all by itself.
So then what makes it be in the thing?
That means it can't live by itself. It has to have an interval around it that is in your set. Essentially, it's not exactly an interval, but you have to have an infinite number of points from the set that are really close to it. So every interval around your accumulation point contains points in your set. That's what it means.
This is like the example of a removal discontinuity, where you have the one on the outside and you have all the others.
Yeah, that's exactly what it's going to look like. Mhm. So since X naught is not an accumulation point of E, I know there exists a capital N in the naturals such that for all n greater than or equal to capital N, Xn equals X naught. It has to be equal to X naught. It can't be different from X naught because only a finite number of the terms are allowed to be different according to the definition for an accumulation point. Okay?
So the reason why X is here is because X constitutes X.
Well, because this sequence converges to X naught.
Yeah.
And the only way that it can come over here, maybe it's over here. I'm going to change the color. Let's see, where's my color on here? It's right here. Let's make it red. So maybe it's over here, and then it's getting closer, and it's getting closer, and it's getting closer. At some point, it has to jump in here, but it can't be in the pond, so it has to jump straight on over. And then it just keeps repeating itself. It's that point over and over and over again.
What's the both of these?
Yeah, everything has to be in E.
That's probably not this
Yeah. Does that sort of make sense?
Wait, is this explain X naught is not an accumulation?
Yes, X naught is not an accumulation point.
What would be the effect of the
Then they just get arbitrarily closer and closer and closer without actually being equal to X naught.
But I thought you said that an accumulation point could be in this set.
The accumulation point in the set, if it's actually an accumulation point in the set, then it has to have a sequence converging to it that is not equal to itself. So it's just the limit of a sequence different from itself.
So if the sequence doesn't happen,
Then it doesn't matter. You have to have a sequence converging to it whose terms are all different from the limit. All, you can cut the first few terms off if you need to, but you just have to be able to come up with some sequence that converges to it whose terms are different from it. So if it's not an accumulation point, then after the first finite terms, all the terms have to be that value. They can't all be different. You still have to have the sequence coming to it, but an infinite number of those terms have to be equal to it. Mhm. Okay, so what happens then? I'm going to fix my epsilon greater than 0 because it says I have to show that this has a limit. So this is like section 2.3 or so. Fix epsilon greater than 0. Then for all n greater than capital N, if you look at f of xn minus f of x naught, f of xn is equal to f of x naught, so I'm just going to plug in f of x naught there. What is f of x naught minus f of x naught? 0. 0 is certainly less than epsilon. Thus, the limit as n goes to infinity, f of xn is equal to f of x naught as desired. Yep, that's all that one is.
How does not accumulate then f of x n is equal to
Yep, because xn equals to x0. I did. I spent a lot of time saying xn was equal to x0.
I got a question like that on the test as well.
I don't know. It's something like that has been on the test. I don't think I've given that particular one on the test, but if I do it in the lecture, it's fair game. Everything's fair game almost.
Wait, are these as cumulative or is it only from like where we stopped for the last time?
They're not cumulative. It's, yeah, where we stopped on the last one. Which was all of chapter 2, right? 2. Yeah, soon, but not quite yet.
Not quite.
Not quite.
I like that, not quite.
Okay, let F take e to r with x naught in e and x naught an accumulation point of e. Then 1 through 3 are equivalent. This is the first time we're using this term equivalent. Equivalent means that they mean the same thing.
Like 1 plus 2 equals 2 plus 4?
Similar to that, or that 1 implies 2, 2 implies 3, and backwards. 3 implies 2, 2 implies 1, or 3 implies 1, and 3 implies
So it's
2.
more like the associative,
Like-
like A plus B plus C equals A plus B plus C.
Mm-hmm. Yeah, that you just have to realize that they mean the same thing. They literally mean the
Like
same
all
thing.
of them, like
All of
the
them-
combinations will be the same thing.
They all mean the same thing. So if I tell you f is continuous at x naught, then you immediately know f has a limit at x naught, and the limit as x goes to x naught, f of x equals f of x naught.
You were proving this. Did you use the second one to prove
In
the
fact,
first?
you actually have to start with each one to prove the next one. So I'm actually going to prove it
I got
in-
proof of
What,
it.
what was it? Like, not putting this in,
You have to do an F elevator to do this?
no. Okay, well, watch. Because what I'm going to do is I'm going to show that 3 implies 2, and then I'm going to show that 2 implies 1.
Oh, okay.
And then
Not-
1
not-
implies
not-
3.
If I was proving that 3 implies 2, and we got to that result, can you use what you already used to prove like 2 implies 1 and 3?
You can go back and use 3 because you know it's equivalent to
Yeah,
2.
that's what I'm saying.
What people in that case, if you're going to need to use 3 to do 2 implies 1, they usually just go back and do 3 implies 1. So if you get 3 implies 2 and 3 implies 1, then you just have to do 1 implies 2. And then you've completed your circle. So yeah, you can do it, but they usually make it easier and just go 3 implies 1.
So there's like multiple ways. we
Oh,
can
yeah.
do this.
You just have to manage to make a circle all the way through it somehow. Yeah. And you can start with 3 implies 2 and then do 3 implies 1, and then you have to make a connection between 1 and 2 somehow. Mhm. So let's go ahead and, yeah, I wrote down the ordering. Show that 3 implies 2, 2 implies 1, and 1 implies 3. That's the order that we're going to do this in.
3 very similar to the one we just proved.
Yeah, except it's not necessarily not an accumulation point. They don't tell us that, so it's not that easy. So what is the hypothesis that we're given up here, the big hypothesis?
Let all of that.
Yeah, let F take e to r, x naught in e, and x naught is an accumulation point of e. Mhm. So let's go ahead and write that down. Let F take e to r, x naught in e, and x naught an accumulation point of e. Now, I'm going to assume 3. So assume that for every sequence, x n converging to x naught, xn in E for all n in the naturals, we have f of xn converges to f of x naught. So assume we have that happening. Our goal is to show that for every sequence xn converging to x naught, xn and e, so that's our same hypothesis, f of xn, oh, I read the wrong one. I jumped up over my proof. I thought that said 3. Let me jump up higher. F has a limit at x naught, and the limit as x goes to x naught, f of x equals f of x naught. How would I show that we have a limit there? Yeah, but there's something, didn't we have a theorem? Let me see if I can find it. It seems like it was theorem 2 point something. Is it 2.1? That very easily might be it. Yeah. So look at theorem 2.1. It's on page 69 in your textbook. What does theorem 2.1 tell you? Yeah, something very important.
And if there's a limit of x here, it can only get for each sequence with x. Well, the first
Yeah, then, yeah. Well, now they told us that all of these sequences converge to the same limit. So I just have to apply the theorem. By theorem 2.1, f has a limit at x naught. Now, what would that limit be? By hypothesis, they tell me. The limit as x goes to x naught, f of x has to be the value that they all converge to. And that's what you were trying to do. So, part 2 is proved. Yeah,
Are they all short or there's some long?
there's some that are a little longer, but they're not too bad. I'm going to put it this way. Thus, 3 implies 2. Okay, now we have to assume 2. I'm looking at this one now. Assume that f has a limit at x naught, and the limit as x goes to x naught, f of x is equal to f of x naught. Now what we're trying to do is show, ooh, too far. It jumps, it's so sensitive to that. We're trying to show that f is continuous at x naught. How do I show continuous? Yeah, we're going to have to go back to the definition. We don't have any other way to show it. CTS means continuous. Now, how do I show that it's continuous? Fix our epsilon bigger than 0.
That's all.
As always. Yeah, we should be very used to doing that by now. Fix epsilon bigger than 0. And then what did they do? Yeah, we have to find the delta. How do we find the delta? What does part 2 tell us? This is on page 84 in your textbook. I'm not going to scroll back up again. What does part 2 tell you? So by definition of limit, I know there exists a delta greater than 0, such that for all x in E, with, now this is 0 is less than, wait for it, there we go, x minus x naught less than delta. we have f of x, I think I can fit it here, minus, the limit was f of x naught is less than epsilon, right? Well, we're good, except we need to remove the 0 less than. How do I get rid of that? I just have to look and see what happens at 0, at x0, right? F of x minus f of x naught has to be equal to f of x naught minus f of x naught. Well, what is that equal to? 0. And 0 is definitely less than epsilon. So in both cases, I have for all x in E with x minus x naught less than delta, we have f of x minus f of x naught is less than epsilon. What does that tell us? Continuous at x naught. Therefore, 2 implies 1. The last thing that we have to show, I need more space for this one. Yeah. Oh, too far. So we have to assume f is continuous at x naught, and yeah, it gets behind. Well, if f is continuous at x naught, I need to get a sequence of points because it says for every sequence of points. So let xn be a sequence of points. So be a sequence in E, which converges to what? What does part 3 say the sequence needs to converge to? To x naught. And we need to show that f of xn converges to f of x naught. Well, what does it mean for f to be continuous? So let's go ahead and fix our epsilon greater than 0, and then we'll apply our continuous definition. I know there's a delta greater than 0, such that for all x in E, with x minus x naught less than delta, we have f of x minus f of x naught is less than epsilon. Definition of continuous. Now tell me about these xn's. If those xn's are converging to x naught, is there a way to get them close to x naught? Yeah. Since xn converges to x naught, there exists a capital N in the naturals such that for all n greater than or equal to capital N, xn minus x naught has to be less than delta. But if xn minus x naught is smaller than delta, what is f of xn minus f of x naught? Yeah, I don't get to say 0 because I don't know it's 0, but I know it's close to 0. What's our conclusion?
Yeah.
Not quite, almost. F of xn converges to
There you put that on because
f of x.
we're done.
Yeah, there you go.
That's
Put a little box
we're
around it,
done.
that'll be the end.
Thus 1 implies 3, right? And so the statements are equivalent.
Do we have to do this sort of, proof on, or like ever again?
Yeah, you actually will be doing equivalent, but I don't think it's on this homework assignment. So the answer is yes, but not yet.
We'll see it.
Yeah, eventually. So that was our theorem 3.1. The only theorem in this section.
Wow.
Note that the usefulness of theorem 3.1 comes in being able to show that something doesn't converge. So if you want to show f is not continuous at x naught, you find a sequence xn converging to x naught so that f of xn does not converge to f of x naught. That allows you to show it's discontinuous. That's easier than trying to argue. Remember our jump arguments that we were trying to do in chapter 2, and then we went to two sequences that give you different limits? Yeah, this is equivalent to the two sequences that give you different limits. You actually don't have to do two sequences. All you have to do is find a sequence that does not converge to that function value. And then you know it's discontinuous at that point. So let's look at this example right here. This computer thinks it knows better than me. It gets close up there and then it jumps. Show that the function f of x equals x squared minus 1 over x minus 1 if x is not equal to 1, and 6 at x equals to 1 is discontinuous at x equals to 1. Well, let's think about what this function looks like. If I factor this, this is x minus 1, x plus 1, and what cancels? So that's x plus 1 if x is not equal to 1. Well, what is the shape of that graph? That's a line. That's a horrible x. Let's fix it. So that's a line, and it goes through y equals to 1. At 1, it's going to have a hole, and then it keeps going. And now I say at 1, it actually should have a height of 6. Forgive my scale, guys. So we want to show that this is discontinuous. There's a hole there, and you have to jump up to the point. So it looks like it should be discontinuous. That means we have to come up with a sequence so that f of that sequence does not equal to 6. I'm going to say let xn be equal to, and I'll choose 1 minus 1 over n. How does that sound? Then let's evaluate. Oh, this should be in proof format. Yeah, I forgot the show part.
Is this a proof or the knowledge?
No, it is a proof. Anything that says show is a proof. Let f be defined as above.
It's not a show off TV.
No, it isn't. Let xn be equal to 1 minus 1 over n for all n in the naturals. Then xn converges to 1 as n goes to infinity. And let's look at f of xn. F of xn is equal to, it's not equal to 1, so I use the first one. So it's going to be our 1 minus 1 over n squared minus 1 over 1 minus 1 over n minus 1. So the 1 is going to cancel. And let's FOIL the numerator. That becomes 1 minus 2 over n plus 1 over n squared minus 1 over minus 1 over n. The 1's cancel. Yeah, I can invert and multiply by that minus 1 over n. And so you get a minus 2 over n plus a 1 over n squared times a minus n over 1. So that n is going to cancel with one of those and all of that, and the minus changes sign. So that is going to be 2 minus 1 over n. Yeah. Limit as n goes to, yeah, f of xn is equal to 2, which is not equal to 6. Thus, f is not continuous or discontinuous. You like that one? That one's fun. Question.
Why did you decide to let X equal 1 underscore?
I have to have a sequence converging to this point where it's discontinuous at. I could have used 1 plus 1 over n. I could have used
So just anything that converges to 1?
anything that converges to 1. Mhm.
Or did you know beforehand that?
No, it will all cancel out just nicely.
Or anything that converges?
Anything that converges to 1 works. Mhm. Yeah. Nothing special about it.
Just don't choose sign. choose sign.
Yes,
All right, speaking of sign, what?
we got it.
Oh, you had to drink it.
Let's go ahead and with sign and coast.
So
Over anything up with.
show that g of x equals sine 1 over x is discontinuous at x equals to 0. That was where we also showed it didn't have a limit. So how do we show that it's discontinuous? Remember, for it to be continuous, it has to be equal to g of 0. But what is g of 0 equal to?
And five.
Yes.
And be done now.
We are very much done.
What?
By property 2, if g is continuous, then that means that the limit has to exist and the limit is equal to g of 0. So the g of 0 does not exist. Thus, by theorem 3.12, g is discontinuous. You can't get shorter than that.
I think that's the shortest proof we've done all
That was,
semester.
All the first one, my whole life.
Pretty much. Pretty much.
See, that's the type of way that I want to prove things. No
That's the way you want it?
It's just examples.
Really
To
short, sweet,
the point. Okay, we saved the best one for last.
Greatest common denominator.
This
is that what
looks
it is?
terrible.
Yeah. It really isn't too bad. Define f to take 0 to 1 to r to be f of x equals 0 if x is in the irrationals.
Oh, that's.
Mhm. And 1 over q. What? Oh, no one did, so.
And when did one?
just make a symbol.
I'm not important. Well, in our class, we probably could, but then you go out from our class using that symbol
Well, you know, at the
someplace.
beginning,
And
Make sure you use it, then every once in a while use it again, but like less symbols used.
that's what that r minus q is. And 1 over q, if x is in the rationals, equal to p over q, where the greatest common divisor of p and q is 1. So it's in reduced form in the rationals, and p and q are positive. So in chapter 2, example 2.5, we looked at this. F has a limit of 0 at each point in 0 to 1. And if you recall, what we did was we took x in the interval 0 to 1, and we said if x is in the irrationals, we chose a sequence xn converging to x, and xn was in the rationals. And then what happened was this 1 over q part, as q got bigger, that goes to 0. So when you get really close to this x, those q's get bigger and bigger and bigger and bigger, because you have to get fractions that approximate your irrational number, and the denominator gets bigger and bigger to do that. That forces that to go to 0. You guys remember that? We did that a long time ago, it now seems. So that was, we had for each x naught, the limit is x goes to x naught, f of x is equal to 0. Where is f continuous? Yeah, it's continuous when f of x is equal to 0, because that has to be, f of x naught has to be equal to 0.
But how can the bottom one?
How can what bottom one equal to 0? This one? That right there?
No.
This one right here?
Uh-huh.
No, the limit is equal to 0. But as q goes to infinity, 1 over q goes to 0. And so if you think about being in some neighborhood around some x naught here, these fractional expressions, the denominator has to get bigger and bigger and bigger and bigger. And the numerator will also increase, but we're replacing the numerator by 1. So the denominator keeps going, and that goes to infinity, which gives it to 0. Yeah. So where is f of x equal to 0? On the irrationals. Yeah. So f is continuous on the irrationals. It doesn't seem like it should be, but it is. Because that's where f of x naught has to equal to the limit. That was our second property in theorem 3.1. The limit of your sequence has to be equal to f of the value. So you have to only plug in the values where your limit is going to be 0. So that's the irrationals. We are done for today. That one was a fun example.
One notice now, that's where we're seeing we all consider, wasn't just one, 2, 3, 4.
Where? Where's your pyramid? Oh, yeah. Yeah. There we go. Yeah, sure
We're
enough.
all happy today. 9 of us. No one missing.
Awesome. That's exciting.
Also, guys, we have